This video is about Big Idea 6, and it's really got 3 big parts, so I'm going to start from the beginning and work my way. The first thing we learned is that when we have an equation, every equation has some sort of k value, that equilibrium constant. And this is going way back. Equilibrium constant, we learned it could be a big number or it could be a small number. The big number means it's product favored, and the small number means it's reactant favored. We also learned that we can do things with k, like add them up. Like if we have an equation, we want to add another equation to it. So equation 1 plus equation 2. Well, if you're going to add the two equations, then really what you're going to do is you're going to multiply their k's. K1 and K2 of both equations. Or let's say you wanted to flip an equation. Then you have to do the inverse of the k, whatever that equation had. The other thing we learned is if we wanted to times an equation by like 2 or 3, that meant you had to take the k and you had to square it. So that's the first stuff that we learned, just basic k, which I think you're pretty comfortable with. When we moved on from that, we learned about Le Chatelier's principle. So when we're looking at Le Chatelier's principle, remember that there's 3 big things that we can do to change which way the reaction is proceeding. Well, I should say that differently. K is always products and reactants. K is always big, so it's products favored. K is always small, it's always reactant favored. But we can push to make more products or to make more reactants. The 3 ways we can do that is by changing concentration, we can change pressure, or the third thing is we can change temperature. So going up here with Le Chatelier's principle, if we assume these are aqueous, what I can do is I can maybe like increase A, and that'll make A too heavy, therefore K will not be there, therefore Q is now less than K, and the reaction has to proceed towards the products in order to make more of the products, and thus get Q equal to K again. In other words, you're back at equilibrium, K. So changing the concentration will force more products to be made, or you can force more reactants to be made, whichever way you want to go. One thing to look at with this thing is we have to think about dilution, because I think you can do well with this idea of changing A or B or AB, but dilutions are a little bit trickier. So let's write the K expression for my A plus B equals AB. Products over reactants, AB over A times B. And then think about it as a dilution. Like let's say I take all these volumes and I dilute the entire reaction by 2. In other words, I have it twice the volume it is before. So then you've got the same number of moles divided by twice as much volume. If you do that, in this case, it kind of cancels out that these are like 1/2 and 1/2, so they kind of cancel each other out. But here I've got a 1 over 2 in the bottom. So suddenly this whole thing is K, but now I've got 2K, because that 2 is dividing on the bottom, so it brings it to the top. So no longer am I at equilibrium, I'm twice the equilibrium situation. If you're twice the equilibrium situation, this is really your Q. Suddenly my Q is greater than my K, and I can't have that going on. So the reaction has to fix that. It'll shift the reaction towards the reactants to remake K. No matter what you do with concentration, no matter what you change, it will always make K again. Moving on to pressure. Pressure, when we think about pressure, lots of times we think about volume. So I'm going to take my volume and I'm going to increase the volume. If you increase the volume, what you're doing is decreasing the pressure. You're creating a bigger area for things to live in. So the pressure is decreasing. So what happens with that? I like to think of it in a more simplistic sort of way. So if I go up here and change all of these to gases, I can see that I have 1 mole of gas on the right and 2 moles of gas on the left. If I'm making a bigger volume, that means I've got a bigger amount of space. It's going to move towards the reactant side, because there's 2 people who are living here, and there's only 1 people who are living here. If I have a bigger space, why not have more people live in that bigger space? It'll shift to the reactants. But another way we can explain that is by once again taking a look at the K. In this case, I'm doing partial pressure, so remember that's the little p situation. So the partial pressure of AB and the partial pressure of A times the partial pressure of B on the bottom. If I'm going to make a greater volume, that means the moles that are living in is a bigger space, so my volume is kind of like the concentration is down by 2. In that case, once again, we've got this situation. Things are looking a little bit different. And in that case, so in that case, I've got another 2K. Well, really, this is equal to Q. So again, my Q is greater than my K, so it must shift to the left in order to remake K. So you can explain it better in this way by dealing with Q and K. Either way you go, once again, you're going to make K again every time. You must get back to K. That's different when we think about temperature. If we're going to say that this A plus B is an endothermic reaction, if it's endothermic and then let's say I increase the temperature. If I increase the temperature, then my reactant side is kind of too heavy. Because my reactant has the heat, because it's an endothermic reaction. If the reactant side is like too heavy, quote unquote, then it's got to proceed towards the products to make a new equilibrium. So suddenly I have a new K. A different way to think about it is if you have exothermic reaction, and then you wanted to increase the temperature. Then your product side is too heavy, so it has to shift towards the reactants in order to make a new K again. Once again, we're looking at a new K. K is temperature dependent, and that all goes back to the kinetics chapter, which you really don't have to know the specifics about that, but we're always going to be making new K when we're dealing with temperature. So it's temperature dependent. That's a key spot. So now that we kind of covered those things, we've got to move ourselves to KSP. Positive. The next big topic we talked about is KSP. That's the idea of a solubility product constant. That's when you take something like AB and it breaks down into its ions. So I'm going to kind of make this different and go AB2 here. This is my solid and here are my aqueous ions. So in a solubility product constant, you have a solid and it makes its aqueous ions. Most of the time, you're going to be dealing with KSPs that are small. And that's because most of the time, this is going to act as a solid. It's insoluble when it's a small KSP. That's usually called insoluble. So the things with KSP is just knowing the idea that KSP is small, it's insoluble. If KSP is big, that means it's really soluble. It means it likes to dissolve. And what we do with KSP is a lot of different kinds of math sort of things. So thinking about the math that we did, the first math that we looked at is just kind of simple. Like, can you find the molar solubility? If they ask you find the molar solubility, that's when you're just taking KSP and you're writing it in its basic form. So if I'm looking at this example here, it would look something like this. KSP equals the two ions multiplied together. And then in that case, you would take the KSP, would have some sort of number. This would be x, and this would be 2x, and you'd square it, and then you'd solve for x. Its molar solubility would be u solving for x. Whatever you get here in moles per liter. The second thing that we were dealing with is ice tables. This is when I finally started introducing ice tables to you. And in that case, you're going to be writing the KSP again. And there you're going to be dealing with the equation. Here we don't have to worry about the solid because we never deal with that in K equations. And a lot of times you might say that this is x and this is 2x. And then in an ice table you're going to be dealing with some sort of change. Like you're going to add a common ion. Like maybe you're going to be adding A to it. Then you're going to add, I don't know, 0.2 molar of that and none of the B. Then you're going to deal with x plus 0.20 and you got 2x here and you're going to put it back into your KSP expression. That's when you're going to say to yourself, okay, most likely 0.2 is going to be much greater than x, therefore I don't have to quadratic equation it and I can solve from there. The last thing that we did with the math part is we dealt with QSP. In other words, we asked ourselves, do I have enough ions in the solution? So there I'm going to calculate QSP because I'm really questioning, like, am I at K, or am I less than K, or am I greater than K? What kind of value am I in? That's when I usually did these big brackets, and we would solve for the total volume on the bottom in liters, and then we'd solve for the specific kind of ions on top. And see, did I get an actual Q? If my Q is equal to the K, then we're at equilibrium, and no solid is going to happen. Because there's not enough ions in solution to push it to make a solid. But if my Q is greater than K, just like with the Chatelier's principle, then yes, you're going to get a solid. Because you have enough ions, too many ions in fact, that it must shift to create more solid. If Q is less than K, then no solid will be made, because you don't have enough ions in solution, so it can't actually make its solid product. Positive. The last thing we talked about was acids and bases. So the first thing is knowing the difference between an acid and a base. Acid produces H+, and these are the strong acids that you have to memorize. A base is the opposite. It produces OH-, or it can take on a hydrogen. Both definitions are good definitions of bases. You only have to follow one definition in order to become a base. So you either produce OHs or you take on an H+. Either way, you're a base. And a strong base is anything where you have a group 1 or group 2 ion, so that's the alkaline earth metals, plus an OH will make a strong base. If we're thinking about acids, that's when we're dealing with Kas. The basic idea of Ka, and this is on your equation sheet, is where you've got an acid on the bottom, and then our H plus and A minus on the top. That's because we're thinking of some sort of acid plus water is going to make the H plus and the A minus, or really H3O plus since I've got water here. So this is your Ka expression. Similarly, when we're thinking about a base, we're going to be taking the Kb, and here it's got to be making OH minus. And it came from something that took on an H, so this A minus right here, and it would make the conjugate acid. Now, if we're thinking about Kas and Kbs, if Ka is small, once again, it's reactant favored. That means it's a weak acid. Weak acids will stay together. If Ka is big, then you're looking at a strong acid, and a strong acid would be these ones. Same thing over here. Kb, if it's small, we're looking at a weak base, and Kb that's big is going to be our strong base, and that would be these ones right here. We can relate Ka and Kw together. We can take Ka times Kb, and that's going to be equal to Kw. So we can relate the two together easily with the equation that we've got. When we've been dealing with acids and bases, most of the time what we've been trying to doing is seeing how much H plus we're making, and that brings us to looking at pH. So pH, we know, is the negative log of the H plus concentration. Equally, we could think about the pOH and say that's the negative log of the OH minus concentration. But most of the time we're going to be looking at pH. Or another way to look at it is if you wanted to find the H plus concentration, you do 10 to the negative pH value. Now this whole pH thing comes from the idea that Kw is equal to the H plus times the OH minus. And we know Kw is equal to 1 times 10 to the negative 14. And what I didn't talk too much about is what this actually means. This comes from this equation. The idea that water can auto-ionize. It can create H pluses and OH minuses. And that creates a K value. This equation is just like any other equation. It's reversible. And it has a K value like we talked about at the very beginning. And that K value happens to be 1 times 10 to the negative 14. Now, one thing that's kind of interesting with this is an endothermic reaction. So this right here means there's heat on this side. And as we talked about before, Le Chatelier's principle says as you increase the temperature, in this case the heat on this side, it's going to shift or proceed to the right, in this case, and that will increase my K. So that means an increase in temperature will actually increase my Kw, which in the end would create more products, which in the end would create, specifically, let's look at H+. As you increase the temperature, you increase the Kw, which means you're actually going to increase the concentration of the H+. If you increase the concentration of the H+, that means you're more acidic, and that actually means that you're going to have a lower pH, which means it's going to be more acidic than a 7. The Kw is only true 10 to the negative 14 when you're at 25 degrees Celsius. If you're going to increase to something like 30 degrees Celsius, you no longer have a pH of 7. You're now going to have a pH that's going to be lower than 7 because of this whole reason, which is an interesting part. So neutral doesn't necessarily mean that it has to be at 7. Neutral means that the H plus equals OH minus, always and forever.
Awesome.
So most of the time when we've been dealing with the math of just like the basic part, we've been looking at the ionization of any like acid or base, so weak acid or weak base. So I'm just going to look at the acid side. So that's when we ask ourselves, okay, if I have 0.1 molar solution of something like HF, then I want to know what's the pH of that solution. Well, in that situation, then we're going to be dealing with the Ka, because really I've just got HF and water. So then I'm looking at the bottom of HF, H plus, and A minus up here, or in this case it's F minus. So here I'm going to have a Ka value, that's some sort of number I can be given. My HF down here will be 0.1 molar, because that's what was given. And then this on top part is X and X. This is where we've got our X squared divided by 0.1, and I can actually solve for what my H plus is. H plus is going to be some sort of number or the other. And then I can convert that to pH, and it's going to be something that's lower than 7, because it's going to be acidic. I can also ask myself, what's the percent ionization for that one? And as a reminder, they love to do that one. That's what I'm going to be looking at. How much HA do I have at the beginning? This is your starting number. In other words, that'll be 0.1 in this example. And then how much H plus do I have, my concentration? And that would be this number here. I'm going to find it as a percentage so I can get what percent is ionized for each part. As a reminder, as you increase the concentration of your weak acid, like HF or whatever it might be, HA, then you're actually going to decrease your percent ionization. And that's just because of the relationship that for every one of these that goes in, 2 of them break up. So you can't maintain your K without that situation going on.